Hey everyone, and welcome to this explainer. Let's just dive right into this, because today we're looking at something absolutely mind-bending in the world of AI training. Now, if you grew up playing older video games, you might actually remember that game AI was often trained using genetic algorithms or evolution strategies. And honestly, it kind of felt like the natural path to artificial general intelligence, right? After all, evolution is literally how human intelligence developed. But for the last decade or so, evolution strategies seemed like a totally dead optimization method, like utterly abandoned in modern large language model literature. Well, prepare to be shocked because evolution strategies have suddenly emerged from the grave. They are making a massive comeback to challenge the very foundations of how we train AI.
For years, the deeply held assumption, like the absolute golden rule in the AI community, has been that backpropagation and gradient-based methods are the only way to train large language models. If you wanted to teach a model, you absolutely needed a teacher signal at every single token. But what if that assumption is fundamentally flawed when it comes to reasoning and reinforcement learning? What if an entirely different approach, one that completely discards the insane memory demands of backward passes, is actually the key to unlocking the next level of AI performance?
So here is our roadmap for today. First, the ES comeback. Second, parameter versus action space. Third, the billion parameter bottleneck. Fourth, enter eggroll and LoRa. Fifth, eggroll versus GRPO. And finally, number 6, hardware scaling.
Let's start with Section 1, the ES comeback.
Looking back at the early days, deep learning researchers actually used genetic algorithms to train neural nets to play Atari games. But those models only had about 2 million parameters. Tweaking 2 million interconnected knobs randomly and just hoping for improvement was, well, it was literally worse than gambling. Mutations usually just scrambled the model's behavior entirely. The signal was completely buried under noise. Then, in 2017, OpenAI published a really pivotal paper using basic Gaussian noise to slightly nudge all the parameters, averaging out that noise over hundreds of models to find useful directions. But even that couldn't scale to modern LLMs. Actually, it wasn't until September 2025 with the ES at Scale paper, and then the absolutely incredible eggroll paper in November 2025, that this method finally became a scalable solution for billions of parameters.
Now, you might be sitting there wondering why go back to evolution at all when gradient descent is so incredibly good at next token prediction? Well, next token prediction has a super clean, differentiable teacher signal for every single word. But reinforcement learning fine-tuning for LLMs, like getting a model to solve a really complex math problem, is the exact opposite. RL involves long-horizon, outcome-only tasks. You might only get a single binary reward at the very end of a massive generated answer. Standard gradient descent really struggles here because token-level credit assignment is just incredibly complex. Think about it. How do you know exactly which word in a 500-word essay actually earned the reward? Evolution strategies, they don't care. They treat the model as a black box, only needing a reward for the whole outcome, which provides much larger and theoretically stronger parameter updates.
Moving on to Section 2, parameter space versus action space. Okay, this definition is absolutely crucial to grasp. That September 2025 breakthrough shifted the entire focus to parameter space exploration. When we talk about this, we mean we are literally perturbing, or slightly altering, the model's reasoning behavior itself. We are actually changing the weights underneath, creating variations of the model that might suddenly become more concise, more verbose, or, and this is the holy grail, even discover an entirely new reasoning approach. Traditional RL methods like GRPO operate in what we call action space. In action space, the model's internal reasoning structure is completely unchanged. You're essentially just rolling the dice to sample variations of what the model already knows. It's totally restricted to a pre-existing sampling distribution. But parameter space, which is used by eggroll, actively discovers new reasoning behaviors by changing the structural parameters themselves. And this is exactly why parameter space exploration can break through standard performance ceilings where traditional token-level randomness just gets stuck.
Section 3, the billion parameter bottleneck. For years, it was this massive myth that evolution strategies could never scale to modern LLMs. People thought exploring the parameter space of billions of interconnected weights would require literally infinite compute. But imagine you're standing on a massive, high-dimensional mountain with billions of possible directions. Most directions are flat or maybe downhill. If you randomly take just a small number of steps in different directions, a few of them are naturally going to tilt uphill. Because massive neural networks actually behave much more smoothly than people expect, when you average those steps together, all that downhill noise just cancels out, and the uphill signal is strongly reinforced. You don't need to map the whole mountain, right? You just need to estimate the local uphill direction. And the truly fascinating number in this whole breakthrough is 30. No way, right? All prior works assumed you needed to perturb tens of thousands of models to find that uphill direction. But researchers found you only need a population size of 30 models. This represents a massive 300 times compute reduction. The global signal and RL fine-tuning is so well aligned across many parameters that a population of just 30 is enough to clearly show real improvements.
All right, section 4, enter egg roll and LoRa. So running 30 full forward passes of a billion parameter model for every single update is still insanely expensive. So a brilliantly named paper called Egg Roll solved this with some seriously clever engineering. Instead of randomly perturbing the entire massive weight matrix, which would be a nightmare, they structured the perturbations as low-rank adapters, or LoRa updates. And here is the magic trick. You can compute just one forward pass of the main model and efficiently swap in the different LoRa's to evaluate the perturbations. You basically reuse almost all of the compute across parallel generations. And the absolute best part? Even though each perturbation is low rank, when you average them all together at the end, you still get a rich, high-dimensional update. It's brilliant. Section 5, egg roll versus GRPO. When we actually put their architectural requirements head-to-head, for all you AI practitioners out there, a really stark difference emerges. Standard gradient descent, like GRPO, absolutely requires both a forward pass and a highly expensive backward pass to calculate gradients. This makes its memory overhead very, very high. Egg roll, on the other hand, operates entirely in inference mode. It only needs forward passes. Literally zero backpropagation is required. This makes egg roll incredibly hardware-friendly and highly efficient on memory, meaning you can run it on setups that would literally crash and burn if you tried to run standard GRPO. And this efficiency translates into absolute dominance in wall clock throughput. Check this out. When tested on the GSM 8K math reasoning benchmark, using an RWKV 7 billion parameter model on 8 GPUs, GRPO could only manage 256 parallel generations. Egg roll, meanwhile, it ran a staggering 8,192 parallel generations. I mean, that's wild. Because it's free from the massive memory burdens of backpropagation and structures everything around inference-friendly LoRa's, egg roll scales beautifully. It allows for drastically more exploration per minute. So the crucial question is, what does all that extra exploration actually buy you? Performance. On the Countdown benchmark using the exact same hardware and the exact same wall clock time, GRPO achieved a 23% validation accuracy. Egg roll achieved 35%. Now, it's important to be neutral here. Researchers note this doesn't necessarily mean egg roll's underlying algorithm is inherently smarter than GRPO token for token. Rather, egg roll's immense throughput advantage means it can simply afford to explore a vastly larger space of possibilities in the same amount of time, outcompeting GRPO through sheer efficiency. It's a numbers game, and egg roll is winning it. Finally, Section 6, hardware scaling. Okay, to sum up what you should really take away from this explainer today. Evolution strategies are surging back to the forefront because they perfectly bypass modern bottlenecks. By completely eliminating the need for backpropagation, they allow for highly parallelizable generations that are incredibly hardware-friendly. You are essentially training in inference-only mode, and strategically, because ES only needs a single overall outcome score, it completely solves the agonizing credit assignment problem in reinforcement learning, where reward signals are incredibly sparse. It's a total game changer. And that brings us to a massive shift in how we think about AI engineering going forward. If we can achieve competitive and sometimes even superior reasoning performance by exploring parameter space without ever running a single backward pass, will inference-only training methods completely rewrite your future hardware demands? It's definitely a provocative thought, and one that should have every single AI practitioner entirely rethinking their GPU cluster strategies right now. Thanks so much for joining me on this explainer, and keep exploring.